Hi all, and welcome back to the ODI Fridays lunchtime lecture. Today we will be hearing from Piers Keane, who will be telling us about whether ophthalmology could be the first branch of medicine to be fundamentally reinvented through the application of AI. Piers Keane is a consultant ophthalmologist at the Moorfields Eye Hospital and associate professor at UCL Institute of Ophthalmology. Piers is originally from Ireland and received his medical degree from the University College of Dublin. So,
thank you.
All yours.
Thank you. So first let me say it's a great pleasure to be invited here for this lunchtime lecture series at the Open Data Institute. And I'm going to tell you a little bit about my experiences with artificial intelligence with the National Health Service in the UK. And in particular, although there's quite a lot of hype around AI, I do think it does have the potential to transform healthcare. And one of the things that I'll try to kind of convince you about in the next 20 minutes is that ophthalmology will be the first of all the medical specialties to be fundamentally transformed, and I think could be an exemplar for other medical specialties in how to sort of do AI properly in healthcare settings. Now, before I get into my talk, this is my disclosure. I think because I'm talking about AI, probably the most important is that I act as a consultant for the company DeepMind, and a lot of my research has been with DeepMind. So please bear in mind that I have that disclosure when you listen to the rest of my talk. So I thought I might start by just telling you a little bit about the problem that we face in ophthalmology. So the problem is this. So some people think that ophthalmology is a small medical specialty, that particularly other doctors might think that ophthalmology is kind of a niche specialty in some ways, but in fact ophthalmology is, at least in my opinion, the most important of the medical specialties, and we have some facts to bear that up. So in 2017, NHS Digital released statistics that showed that ophthalmology had overtaken orthopedics as the number one medical specialty in all of the National Health Service in the UK in terms of outpatient clinic appointments. In fact, nearly 10% of all NHS clinic appointments are for ophthalmology, for eyes. And that's a number that's increased by more than a third in the last 5 to 7 years. And in fact, that's about 10 million clinic appointments per year. Now, one of the challenges that we face then as ophthalmologists, and this is not just in the UK, but around Europe and around the world, is that we're kind of drowning in the number of patients that we have. We have a huge number of patients. We have patients with chronic diseases that, for example, if you're diagnosed with a condition such as glaucoma, you require monitoring of that condition for the rest of your life. So one of the challenges we face is seeing people with sight-threatening disease and managing those people in a timely fashion. And some people, unfortunately, can lose sight because they're not seen and treated quickly enough by someone with specialist expertise. And so with that background, I think that ophthalmology is a perfect discipline then to look at applying the latest advances in artificial intelligence to try and really kind of identify those patients with the most sight-threatening diseases and get them treated as soon as possible. Now, when I talk about AI in the context of this talk, really, for the most part, I'm talking about deep learning. And deep learning is, the reason why there's so much hype around AI in the last 5 or 6 years is because of these breakthroughs in applying deep learning to things like image classification tasks. And in 2015, Scientific American listed deep learning as one of their top 10 world-changing ideas of the year. Now, what is deep learning? Well, deep learning is really just another way to talk about something called an artificial neural network. And artificial neural networks are not a new idea. They've been around at least since the 1950s and 60s when they were called things like perceptrons. And artificial neural networks are essentially computational models that superficially, and I underline superficially, resemble the brain in terms of the way that they process information. Now, the key point is that they learn from experience and they're not pre-designed or pre-specified. So the simplest example that I would tend to use to explain this is that if you were training a computer program to recognize a photo of a cat, in the pre-AI, the pre-machine learning, the pre-deep learning, really the pre-deep learning era, what you would do is you would write lots of lines of code to describe the features of a cat. Cat has fur, cat has whiskers, cats have tails, some cats don't have fur, some cats don't have whiskers, some cats don't have tails, and the like. And you try and describe every single feature of what it means to be a cat. Now the problem was, with that sort of feature engineering approach, despite decades of research, it never really got quite the accuracy that was required to recognize photos of cats. Now, in deep learning, we don't do that. In deep learning, if you've got enough photos of cats and if you've got enough computing power, you essentially present images of cats to a neural network and you say, this is a cat, this is a cat, this is a cat. And the neural network will create this kind of abstract hierarchical representation of what it is to say, this is a cat in a picture. Now, that's I think the basic concept behind it. And it doesn't take, I think, a genius to realize that could be applied across multiple domains. So in the tech world, that's image recognition, speech generation, and even beginning to be used in things like self-driving cars. Now, in healthcare, it's simply oftentimes training these neural networks to be able to identify diseases on medical images. Now, my involvement in artificial intelligence really began when I was reading about the advances in deep learning in the tech world in sort of 2014, 2015. And then when I contacted DeepMind in 2015 and said, we are dealing with huge numbers of patients, we're struggling to get everybody seen in a timely fashion, and we should use deep learning to try and identify those patients with sight-threatening disease. And so in the middle of 2016, we announced the formal collaboration between Moorfields and DeepMind. And of course, for probably many of the people listening, DeepMind are one of the world's leading artificial intelligence companies. They were founded in 2012, and 2 of the 3 co-founders are graduates of University College London, which is affiliated with Moorfields, where I work. And 2 of the 3 co-founders are from London. And so I think that sort of proximity to Moorfields Eye Hospital and that sort of shared experience was the reason that I contacted them. And so DeepMind were acquired by Google in 2014, reputedly for £400 million. And now they're based in King's Cross, and they have this large collection of research scientists working in this space. And so that's really facilitated a lot of this collaboration. Now, what are the applications then in ophthalmology more specifically? Well, we've essentially been applying deep learning to these things, which are called OCT scans. And OCT stands for optical coherence tomography. And in effect, these are kind of like an ultrasound of the eye, but instead of measuring the echoes of sound waves, they measure the reflections of light waves. And in doing so, they're much, much higher resolution than an ultrasound. And in fact, the resolution of an OCT scan is about 5 micrometers. So it's an order of magnitude better resolution than a CT or an MRI scan in this 3-dimensional imaging modality. So if people come to Moorfields and they would, I'm giving them a tour, I would often get them to have an OCT scan of their eye, because there's no radiation, there's no harm in having these scans. So whether you're a 5-year-old or a 95-year-old, you can have OCT scans done quickly and easily and safely. Now, the problem then, of course, is that OCT has become the dominant way that we diagnose eye diseases, in particular retinal diseases. And so at Moorfields, where I'm a consultant, we do more than 1,000 OCT scans per day. And so one of the problems is having the people with the requisite expertise to be able to interpret and make decisions on those scans. And again, bringing in this point of just a huge amount of patients and amount of data that we have to meaningfully deal with. Now, the collaboration started in the middle of 2016, and so we had to go through a long process where we had to think about how do we take these OCT scans and how do we get these historical scans how do we anonymize them in a robust fashion, and then if we're sharing NHS data with a company such as DeepMind, which is owned by Google or Alphabet, what are the considerations around ethics, information governance, patient and public involvement, transparency, and there's a range of these questions that we had to deal with, and we're continuously trying to learn about what is the best possible practice in that type of collaboration. Now, in any event, we were able to share these historical OCT scans and begin training this algorithm, and in August and September of 2018, it was really amazing that we could publish the first results of this, and it was published in the journal Nature Medicine, which is a career highlight for me. It's one of the leading translational medicine journals in the world. And what you can see here is that there's 34 different co-authors on the paper. So it's a paper jointly led by myself and a guy called Olaf Ronneberger, a senior scientist at DeepMind. But it also has senior clinicians from Moorfields, it has scientists from UCL. And one of the things that I've learned is that what was special about this collaboration is that it was bringing together lots of people with lots of different domain expertise. And I really don't think it would have worked if any of one of those pieces had been missing. Now, it was not only published in Nature Medicine, but it was very exciting because it was on the cover of Nature Medicine. And then, of course, this being artificial intelligence, you can't escape the hype around it. So you can imagine how exciting it was to be going home in the tube and see headlines like that, facing you, and you can imagine how exciting that was for my family and my parents in Ireland, and how much of kind of boasting about their genius son who was doing all these amazing things and posting on Facebook and all of those things, which is amazing and exciting, but also a little bit awkward, because I think it's important to highlight that we haven't saved the sight of a single person yet. And so what we've done in this Nature Medicine article is do a proof of concept on a retrospective historical data set. Got really, really amazing results, but now we're entering into a process where we're actually thinking about how do we further validate it, how do we implement it in real life. And so if you come to Moorfields, this is not actually being used in patients yet in Moorfields. And while we're very excited about the potential of AI, we're also suitably cautious. And we feel that we don't want to start using these tools in real life until we're sure that they're safe and that they're accurate. So I just always like to highlight that caveat. In any event, what did we do? Well, we created a neural network framework with two neural networks in series. And what you can see on the left of the diagram is you start with the raw three-dimensional OCT scan, which is essentially a three-dimensional grid of about 65 million numbers in a three-dimensional grid. That's fed into a segmentation network. And so what that is that we've trained a neural network with about 900 OCT scans where a team at Moorfields have spent many months manually delineating every little disease feature on the scan. So every little bit of fluid or blood or scarring on the scan. And that trains a neural network to create a tissue map. So it highlights all the kind of disease features on the OCT, which is then fed into a classification network. And that's trained with about 15,000 diagnosis labels of different retinal diseases. So that ultimately, the output of the two neural networks in series is a referral suggestion, such as urgent, non-urgent, routine, or observation. And then it looks at about 10 different disease features. Choroidal neovascularization, macular edema, all of these diseases that ophthalmologists get very excited about and that a retina specialist would, like myself, would be expected to make a diagnosis of. But a key point is that the number one application of this is not making the diagnosis, it's triaging of the patients so that we can do this type of scan on people in the absence of a retina specialist, highlight those people who need to be seen by the retina specialist urgently, and then that person is the person who would ultimately make the diagnosis. So I think that we're still many years away from a situation where someone would receive an injection in their eye or laser treatment purely on the decision of an algorithm without a human in the loop. Now, here's an example of the prototype algorithm in action. So what you can see down here on the bottom row is the raw OCT scan. It's a three-dimensional scan. And then what's happened is the segmentation network is now delineating up to 15 different disease features on the scan. And you can see this is actually a patient, a man in his 40s who's got poorly controlled diabetes. And he's developed something called diabetic macular edema, which is waterlogging of the retina, which I don't think you need to be a retina specialist to see that that's a kind of soggy retina. And given that the retina is such a delicate structure, that can have really major deleterious effects on vision. And so here then we see maps of the fluid cysts in the retina. And then up here it says diagnosis probability macular edema 98.5%. And in this case we've trained it or calibrated it so that it would recommend a semi-urgent referral to see someone like me or other ophthalmologists in the NHS. Now, so when we trained it, we then had to evaluate its performance. And so what we did was we got data from 1,000 patients who had an OCT scan at first presentation to Moorfields that had never been seen by the algorithm during the training process. And then we ran the model on that independent test set of 1,000 cases, and we looked at the errors on the referral decision and the errors on the different classification tasks. But focusing on the primary output, which was the referral decision, we found that ultimately it had errors on referral decision of about 5.5%. So lower is better. So 0% would be the optimum. And that's looking at the OCT alone. Now, we wanted to compare that against human expert performance. So we got 8 human experts here. Experts 1 to 4 are consultant ophthalmologists at Moorfields who are retina specialists, some of whom are world-famous retina specialists. And experts 5 to 8 are optometrists at Moorfields who have some experience in looking at OCT scans but wouldn't have quite the same level of expertise. Now, how do you think that they did? Well, it turns out that the algorithm did better than all 8 human experts, except for experts 1 and 2, where it did better, but it wasn't statistically significantly better. Now, that was exciting. A couple of points you might wonder about is, why has expert 8 got a 24% error on this referral suggestion, and what's going on there? It turned out that this was a junior optometrist, and they were not missing the urgent cases for referral to a retina specialist, but they were over-referring non-urgent cases. So they were kind of trigger happy on the referrals. So anything that they were even a tiny bit worried about, they would refer in. And that's why they had so much errors. Now, that's exciting. All of this is exciting, but there's a big caveat to it. The big caveat is whenever you see AI beats the best doctors or superhuman performance, a lot of the time when you dig beneath the hype, you see that the doctors are doing something or the healthcare professionals are doing something that they don't do in real life, or they're doing something that they do in real life but with one arm tied behind their back, effectively. So it's not a fair comparison. So in real life, the human experts would never ever look at an OCT scan in isolation. They would have a retinal photograph, they would know the visual acuity of the patient, they would know the presenting complaint or some other details of the history that they would use to help prioritize the referral of the patient. So to make it as fair as possible, we repeated the exercise. We got all 8 human experts at a separate point to look at all 1,000 cases again with a lot of additional information. And
it wasn't perhaps surprising then that improved the performance of all the human experts. And in fact, the number one expert, and this is a world-famous ophthalmologist with more than 20 years of experience, got down to 5.5%, which was the same as the algorithm using the OCT scans alone. Now, as a matter of interest, giving the algorithm the additional information didn't really provide much additional performance over the OCT alone. Now, what did it get wrong? Well, I won't go into the confusion matrices here, but the key point that the BBC picked up on was AI did not miss a single urgent case. And this is me in Moorfields pretending to examine a patient of mine, Elaine Manna, who's been a wonderful advocate for the research that we do. Now, what's interesting is you may say, well, why did the best expert have a 5.5% error rate? Turned out when we looked at the best expert, the ones that he or she got wrong were very ambiguous cases. And actually, it might be the case that our reference standard was wrong and the expert was correct. Now, what was interesting, that held true for the best expert, but it also held true for the algorithm, where a lot of the ones it got wrong, actually, with the benefit of hindsight, we think it might have got it right. Now, why do I think that this is interesting? Well, for lots and lots of reasons, but one thing that I think as a slight tangent that it's interesting for could be medical education. And so I read this book from Gary Kasparov, a very, very good book about where AI ends and human creativity begins. And I think one of the last chapters of the book, he describes like the aftermath of losing to Deep Blue. And he said, well, look, after that, people didn't stop playing chess. And in fact, young chess players now learn to play chess using chess computers. And he highlighted that that has had a couple of effects. One of which is that chess players can become better more quickly than in the past. So you've got more grandmasters at a younger age. And you've also got a much wider geographical distribution of chess talent than you had before, which is facilitated by these things. And so one of my interests, side interests, if you like, is, if I'm an expert in OCT interpretation after 10 years of looking at them at a world-famous eye hospital like Moorfields, I'll bet you with the right tools and with the right data, you could get somebody in a different location who could actually become as good as me in 10 months or in 10 weeks, or better than me even in those times. And I think when we democratize things in that way, we're going to get a lot of breakthroughs. So my last 2 or 3 minutes now, before I take some questions, I want to change the subject completely to tell you about something that I am the most excited about, even more excited about than what I've just told you, which is something called automated deep learning. And so what this refers to is a blog post that came out in the middle of September about how Moorfields is using AutoML, which is a product from Google Cloud, to enable clinicians to develop machine learning solutions. Now, why is this something I'm excited about? Well, the problem at the moment with a lot of deep learning is that you need a lot of computing power and you need at least some specialized expertise to train these models. And so for me as a clinician who's not an engineer, not a computer scientist, and working with people like the guys from DeepMind over the last few years, I've kind of always been a little bit in awe of like their technical abilities and their expertise, and kind of wishing that I had done some machine learning training when I was younger and all of those things. But feeling that if I had some of those abilities, I would be able to actually extend the applications of AI in healthcare quite extensively. So it was really exciting for me in November 2017 when there was an article in the New York Times from Kate Metz in the New York Times about something called automated deep learning, or building AI that can build AI. Now, the key point was that a number of companies, Google, Amazon, Microsoft, Baidu, and a number of others, are building these platforms called automated deep learning platforms. And they're essentially application programming interfaces that allow you to train deep learning models without coding experience. And many of them just using drag and drop interfaces. And so what we were excited to do then was to apply those platforms, and we're the first to have done this, in medical imaging. So we published a paper in just about 2 or 3 weeks ago in the Lancet Digital Health, where what we showed was the feasibility of using the Google platform for medical image classification by healthcare professionals from my research group with no coding experience. So what we did was that we got 5 publicly available medical image data sets. So we wanted to use publicly available data sets so we didn't have to worry about data protection issues and the like. So we got publicly available databases of skin lesions for skin cancers, adult chest x-rays and pediatric chest x-rays, OCT scans, and diabetic retinopathy retinal photographs. And the upshot is that using one of these platforms, we were able to get results that were comparable to state-of-the-art with no coding experience and only in the course of hours or days. And I can't tell you how exciting that is for us and the potential for that. So as an aside, one of the questions that came up in the review process at the journal for this was the editor said, one point that we hope you will be able to address in the revision is to emphasize that automatic deep learning tools will not necessarily replace AI experts. Now, I couldn't help but smile a little bit when I saw that, because over the last 3 or 4 years, every talk I've given about AI in healthcare has ended with questions about will AI replace doctors, and I've had to try and kind of bat them away. And so now it's nice to turn the tables a little bit and have to explain why AI experts won't be replaced by some of these platforms. So why am I excited about this? Well, I think that some of these platforms could be a bicycle for the mind. And so there's this nice figure from the 1970s, 1973 in Scientific American, that graphs energy usage per body weight per distance traveled, and it compares a fruit fly to a lemming, to a jet fighter, to a helicopter, and a variety of other things. And it turns out the most efficient is a man or a woman on a bicycle. And this was something that was seized upon by Steve Jobs in the late 1970s and 80s. And this is an advertisement from August 1980. Now, what we forget is that it wasn't really apparent in the mid-70s that a personal computer should be something. And in fact, when Apple started to make the first personal computers and others, there was a lot of people in the computing industry at the time who said, why would anybody want a personal computer? And more, they said, well, we build mainframe computers for large corporations to do the payrolls of those of the corporations. Why would anybody want that in their own home? And secondly, these personal computers are actually very inferior to these mainframes. They can hardly do anything. Like, what's the point? And it's interesting to read some of these sort of contemporaneous advertisements to see what that was like. And in this paragraph down here, he says something like, today, most people are not even aware that a personal computer exists. And what's interesting when you go on to read more about that is he begins to talk, and you see these advertisements with him in the early 80s, where he talks about meeting a geologist in Iowa who's using a personal computer to look at soil samples or to do any number of applications that nobody would have thought of until this technology was democratized. Now, what I think is that automated deep learning could have that potential. And of course, there's loads of hype around AI, and I accept all of that. But I do believe, like people like Andrew Ng, that it does have the potential to be kind of the new electricity and, spur an industrial revolution. So when I give this talk to ophthalmologists, I say, if not you, then who? So I say, look, these platforms, they're free to use, at least for a time. That you can get these publicly available image data sets, and you can go out and actually try this yourself and get going on this. Of course, the caveats I say 2 important caveats. First is, don't use your own hospital's data until you have gone through some sort of rigorous kind of approval process, and information governance sign-off and all data protection impact assessment, all of those things. So that's the first thing. Use publicly available data sets. And the second thing is, for the machine learning community, I say, look, nobody is claiming that these could be used for direct patient care anytime soon. They're clearly not as good as bespoke deep learning models. But actually, in the first part of my talk, I was urging caution. Even with state-of-the-art deep learning models, we have to be very cautious about using them for direct patient care. And we should be doubly cautious if we're talking about automated deep learning models in the future. But nevertheless, what I could imagine is that just by having these tools, there's lots of things you could do that are clinical research tools that don't involve changing patients' care, where actually you could have transformative effects. Now, this is Livia and Siegfried. These are the two researchers from my group who actually are the people with no coding experience who did all the hard work and got to grips with this platform. And so my last slide, because I always talk for far too long, is where are we going with this? Well, I think it's really important to say that AI has huge potential, deep learning has huge potential, but we must balance our excitement and our enthusiasm with a kind of caution and skepticism, and a healthy skepticism about this. This has huge potential, but there's lots of ways that it won't work. There's lots of ways that deep learning algorithms can be brittle or fail to generalize to different populations. So we have to actually think a lot about how we validate these things in the future before we use them in real life. I think as we start to do that, we're going to get a lot more breakthroughs in AI-assisted science. So in particular, can we do novel things that we can't do in care at the moment? So could we use deep learning to predict, acute kidney injury 48 hours ahead of time, or predict the development of the severe forms of macular degeneration 6 months ahead of time? And if we can do that, is there something actionable from that? And then lastly, I think that we are entering an era where we're going to see increasing democratization and industrialization of the processes. So, I happen to think that even if there's no more fundamental breakthroughs on the computer science front, there are lots of applied research applications that we can do without those more fundamental breakthroughs. And so I think we'll see a lot more industrialization of the process. And I think some of these automated platforms are only likely to increase in power and increase in widespread usage. And then lastly, one of the things that I'm very excited about is in the UK is this thing called Health Data Research UK, which has funded a number of health data research hubs around the UK. And I'm working with the Open Data Institute and others to think about how we can share the learnings and the experience from at Moorfields to other eye hospitals around the UK, and how we can think about what is the best possible practice if we're looking at the use of NHS data for development of these tools in the future, and what are the pros and cons, what are the risks and benefits, and what would be the gold standard way that we can do that. And then very lastly, that's my email address and that's my Twitter handle. Thank you very much.
Thank you very much. It was really interesting. So now we can open the floor to a discussion. Anyone has questions? Perfect. If you can also introduce yourself.
Okay, thanks. Hi, my name's Andy German. I work for a company called Guyana, which is not far away. It's sort of codeless AI analytics platform. I'm new at that. I've recently joined from Innovate UK. Yeah. So I thought it was brilliant. Thank you. It's great to see a presentation on machine learning that I can follow all of. So thank you very much for that. So being kind of new to it, getting my head around it, you read about bias and the effect that bias has. So I was going to ask you about your 900 images at the beginning, and then when you get to the 5.5% question. So the obvious question there is: was the algorithm being over cautious or under cautious? Yeah. And then taking that further, how could you use that data to tweak the training set, or the algorithm rather?
Those are a lot of good questions, and some of them are quite profound. philosophical questions. That I think one of the nice things about Moorfields and London and the NHS, Moorfields is the largest eye hospital in Europe, is that we have a very diverse patient population, as well as a large patient population, very diverse patient population. So diverse in terms of different ethnicities and people from different countries. Also diverse in terms of the range of disease severities. So we have everything from the mildest to the most severe disease. And so I think that the algorithm that we've done, we've trained it on a very representative data set. And you could probably find like 100 patients from any given country you could care to think of within the data set. Now, so I'm optimistic that the work we've done will generalize to other applications. So if we start to use it for hypothetically in Manchester tomorrow, I think it would work very well. But I also think if we started to use it in the US or imagine in other countries, it would work well. However, that is not guaranteed. And in fact, it could be that imagine if you have a situation where you have a patient from Ghana with diabetes who goes and has an OCT scan in Moorfields and the algorithm works very well. And imagine that same patient flies back to Ghana, has an OCT scan with the same device in Accra, and you might find that the algorithm doesn't work as well, because maybe the person taking the scans takes them in a slightly different way, or they're not as good as the technicians, or they're better than the technicians who take them in Moorfields. Now, so in other words, it's up to us to prove that. So what we're now thinking about is how do we prove that it'll work well, not just in Moorfields populations, but in those other things. And you could imagine that if we don't do that correctly, or if we're not aware of those risks, you could have risks whereby you develop an algorithm that, in the worst, like imagine a situation where it works best on like white Irish men in their early 40s, okay? But it doesn't work on Afro-Caribbean women in their 60s, something like that. And it turns out that that could be a big problem, particularly when you think of, if we're talking about automated processes and you're talking about working with big tech companies, you're dealing with issues of homogeneity and scale. So maybe it's making the same mistake, but it's making it millions of times. That's going to be pretty bad. So we need to know about that ahead of time. And I guess with humans, you're protected by the fact that although humans make mistakes, and it could be that they're less accurate, humans are diverse in the mistakes that they make. And somehow that kind of helps. So that was my sort of long-winded answer to the first part of your question. The second part was around our algorithm and, was it overcautious or undercautious or trigger happy or, all of those things. And I think that that's something that ultimately the shorter answer is that you have to calibrate the algorithms depending on what the use case is. And so you might want to have a situation where you're prepared to get a lot of false positives because you want to miss a false negative or vice versa. And so, for example, if it's a screening for a disease, you might want to pick up every case and not miss any case. But if you're about to make a decision where you're going to give someone an injection in their eye or do an operation, you might want to have a situation where you're only going to do it on people who you're really certain that they actually have the case. So there's different kind of operating points on the performance of the algorithms. Okay.
Thank you.
Do we have any other question? Yeah. So who goes first?
Thank you. I'm curious about this experience from the patient's point of view. How much do they know about the triage process, and how do they experience it from their point of view?
So, so the thing is that at the just to emphasize, at the moment they are not. This is not being used. We will have to evaluate that in the future to see how will patients mind coming in, having an AI system triaging them and the like, or will doctors or healthcare professionals mind that. And we've got some studies which are looking about those kind of human-computer interactions. But what I would say even before that, the situation is pretty tough actually for patients as things stand. And I think the Elaine Manna's case, which I showed the picture of earlier, it kind of exemplifies why I initiated this collaboration. And Elaine has talked about this publicly. But what happened with her was she's someone who had lost her sight in her left eye from age-related macular degeneration more than 10 years ago before there was good treatment. And about 2012, 2013, she started to develop loss of vision in her good eye. She went to her optician. Optician said, I think you're developing wet AMD in your good eye, the severe form. But the good news is that there's some treatments now that we can give you, to some injections to halt this. I'm going to give you an urgent referral to the hospital eye services. She then gets an appointment 6 weeks later. Now, if that was my mother, I would want her to be seen and treated in 6 days, not in 6 weeks. And so in Elaine's case, she was able to get into the hospital and get seen and treated before that. But the point I'm trying to make is that, that's the challenges that we face with the huge number of patients that we deal with. And so I think when I've talked to patient groups about it, they're very positive about anything which makes the system better.
Okay. Hi, my name is Olivier. With the caveat that I snuck into the room halfway through, so apologies if you've covered this. But I was interested by what you said towards the end about sharing data with others in the NHS. I was wondering, and kind of also building on what you said about the fact that we need a lot of diversity in the data to cover all the variety of people. What would you say are the barriers to getting that kind of data sharing done, but at the international level?
So that's it was a very good question, but it was complicated at the end by at the international level. It's quite hard to do it at the national level. So maybe I'll sort of answer that. I'll readjust your question to answer the first part first, and then maybe pivot to the international part. I think the fact is that if you're talking about, for the most part now, with these AI applications, we don't have the expertise to develop these things entirely within the NHS. So we have to work either with an academic or an industry partner. And academic partners are great, but ultimately, if you want to have something that can be used by millions of people, you need to have an industry partner. Now, so basically what I've had to learn about, or effectively kind of roll up my sleeves and kind of learn about over the last few years, is what are the ethical approvals that are required to do these type of studies? What are the information governance approvals that are required? So how can you demonstrate that you've anonymized the data? What safeguards do you put in place? What are the patient and public engagement and transparency things? And actually what I've learned is that that's the most important. So in other words, one of the things I'm proud of in Moorfields is that we have a section of the website dedicated to the collaboration between Moorfields and DeepMind, which talks about it. It has details if you want to contact us to opt out of the research. When you come to the waiting rooms in Moorfields, there's posters which talk about it. There's the screensavers on the TVs in the waiting rooms show that one of the screensavers comes up, Moorfields, Google DeepMind or whatever. If you want to learn more, contact here. So, when we announced it, we had the Royal College of Ophthalmologists, all the major eye disease charities and the patient groups all kind of supporting it. So we worked a lot on the patient and public engagement side and the transparency side. But even when you sort out all those things, the other thing that you might encounter is people say, well, it sounds like you've done everything right, but one thing is, what's the value of the data? And why should we be giving NHS data to a tech company, and what's the value back to the patients in the NHS in the UK? And so I initiated this collaboration because things were so challenging and people were losing sight, for this specific application. But I think in the coming years, working with people like Health Data Research UK, we can try to figure out a kind of nuanced approach to it, so that we think about what's the best thing that we can do for patients and the NHS using their data. And we can get input from people like the Open Data Institute about what is the best practice in that regard. So those are all the things that I think we need to learn about. If you then say, to answer your question, international context, maybe I'll figure that out in a couple of years' time. Thank you.
Do we have any other questions or questions from home? Or no? Okay, then thank you very much. It was a really great talk.
Thank you.
Thank you everyone for coming.